Okay, this is a recording of the 1 to 5B worksheet. Again, don't pay attention to the date. We start out with problem number 34, in which we're just solving an exponential equation. Remember, whenever we're solving for a variable that's in the exponent, like this t right here that's circled, I cannot solve for that variable until I get the variable down with the other values in this equation. In order to bring an exponent down, we take the natural log of both sides. And in this case, it works really well because the base is e. And the natural log is the inverse function of e raised to. So the natural log undoes the e raised to, and we simply end up with the exponent on this side. Now I showed it coming down out front because the natural log of e is 1. That's why the natural log undoes e. The natural log of e is always 1 because if the base is e, the exponent is going to be 1 to produce an e. So the natural log of e is always 1. 1 times 0.05t is 1.05t. Divide both sides by 0.05t, and we have this for our answer. Here is the decimal approximation. I probably should have used approximated symbol here. Always accurate to 3 decimal places. 36. 36 is like that example that we went over in which we have to do a u substitution here. So the first thing that I do is I rewrote this as 2 to the x plus 1 over 2 to the x. So at least I have the same function, 2 to the x. Now the problem with this is this 2 to the x is making this equation difficult to solve. So let's replace it. Let's replace it with something simpler. Let's call 2 raised to the x u. U is a typical variable that's used, but you could use whatever you want. V, z, any variable. You'll just see this is very common to do a u substitution. So I replace 2 raised to the x with a u, 2 raised to the x with a u. Now this looks a little bit cleaner. I can multiply every term by u to eliminate the denominator, just like I would with any equation that has a fraction. So u times u is u squared, 1 over u times u, the u cancels, and 5 times u produces a 5u. Well, this is quadratic. We know how to solve quadratics. Subtract 5u to the other side, and we hope that it is factorable, but it's not. There isn't 2 numbers that multiply to be 1 and add up to be -5. So we have to use a quadratic formula. You're not going to have to use a quadratic formula a lot. I can't remember the last time I would have seen it on the AP test, if ever. But here it is. Opposite of b plus or minus the square root of b squared minus 4ac all over 2a. I'm showing all of those values coming in. A is 1. B is -5, C is +1. There it is. 25 minus 4 is 21. These are my 2 solutions. For u, I still have not solved for x. So I have to plug this in for u right here. Now how do I solve for a variable that is in the exponent? I take the natural log of both sides. Why? So that I can drop down the exponent of the argument out in front of the natural log. And then I can divide both sides by the natural log of 2. This is the analytical solution, the exact solution, and here are the 2 decimal values. Remember, when you type this into your calculator, just do the positive square root of 21 over 2 first as you do this, and then hit second enter, and all you have to do is come back and change that plus to a minus, hit enter, and you will get this right away without having to type everything in again. Okay? So make sure you're proficient with how to use your calculator to its fullest capabilities. Hopefully this one went well. Probably not going to be on a test or a quiz, but this whole concept here is good to review early. We will do this frequently in calculus, where we replace a more complex function with a simpler variable and rewrite so we end up with a simpler equation to solve, and then come back and just resubstitute back in to the original variable. It's a common practice in mathematics. All right, this one here I think is probably the most important because we're working with those logarithmic properties that we discussed in this section. If I'm trying to isolate y, there's only one term that has a y in it, this first natural log. This term is just a number. That is x. This is the natural log of x. So if I want to isolate y, I need to get all other terms away from the variable. So I'm going to add the natural log of 2 to the other side. That's the first step. In the example, in the notes, I simplified these logarithms first. On this one, I just decided, since I have a natural log in an argument only, I'm ready now to take e raised to both sides. But I can only take e raised to both sides of an equation if one side of the equation is a natural log raised to a natural log of an argument only. Because now when I take e raised to both sides, the e will undo this natural log and will leave me with just the argument, because e raised to and natural log are inverse functions. So if I take e raised to this side, I have to take e raised to this side. I could add 1 to the other side and I would have y isolated. But you'll never see a solution on the multiple choice problems in which they leave the natural logs in the exponent of e. So if we have a natural log and an exponent of e, we need to set ourselves up to undo these inverse operations. They should undo each other. So this step right here, if I could put an asterisk or highlight this, I would highlight this step from here to here is what creates the most problem for students, but it's really just an Algebra 1 rule in reverse. If we multiply like bases, almost everybody knows we can make it one base and add the exponents. We're just doing that exact same property in reverse. We are saying if we're adding exponents, we can treat it as a multiplication of like bases. E to the x times e to the natural log of x times e to the natural log of 2. This step is required for me on your test and quizzes whenever we're undoing e and natural log. It must be written as factors. A lot of students want to go right to this. If you do it on the AP test, you're probably not going to lose points for doing that. But for me right now, I want to see this. Now, e undoes the natural log, so I just end up with x. E undoes the natural log, so I just end up with 2. And these are now factors. They're not terms, they are factors. 2 times x times e to the x. Always write numerical coefficients first, then any polynomial, then any exponential or trig or more complex functions. And then I add the 1 to the other side, and this is the answer. We're going to see this exact same work embedded within calculus problems. And the answer will be simplified like this for all multiple choice situations. If you were to leave the answer like this with 1 added to the other side on the free response, you'll get a point. You'll get the points. But I want you to get used to this practice so you understand how to get this more simplified version of this function. This step right here, I cannot stress enough, from here to here is the most important step that I need to see. Okay? Okay, going to some of the graphs now. 40 can be a pretty tough problem. And I would not be afraid to give you a problem like this on a test or quiz. There's been one very similar to this in the past. Draw the graph and determine the domain and range. Rewrite the logarithm in exponential form and plot at least 3 quality points. Identify any asymptotes and intercepts. So I'm being as specific as I can be with the directions. That's how it will be on tests and quizzes. Okay? So I'm being more specific than what this problem in the book looked like. What I want you to do is to be able to solve for x in terms of y. I want to dig x out of this logarithmic equation. I have a separate term, so I have to subtract 1 to the other side. What some students will forget to do is to eliminate this -3 before they undo the logarithm. I have to divide both sides by -3. Remember, log with no base is called a common logarithm, and it's assumed to be a base of 10. So to undo a log base 10 of an argument, I can now take 10 raised to both sides because I have a log and an argument only. So the opposite of log base 10, the inverse operation of log base 10, is to raise it is to raise both sides to the 10th, or raise both sides using a base of 10. So I take 10 raised to this side, 10 raised to this side to undo this log base 10, end up with this argument of x plus 2, and it will give me 10 raised to this side. I always taught it as just base raised to the exponent equals the argument. It's the same thing. And recently in Algebra 2, they've converted to saying to undo the logarithm, take base raised to each side. And the base here is 10. Whatever works for you to rewrite it like this. Notice at the same time, I changed this around. I multiplied the top and the bottom by -1. I made this negative y plus 1 over positive 3. It just cleans up these negative signs here, so I don't have as many negative signs. You could have left it like this. Subtract the 2 to the other side, and I think this is the best form of this exponential function. Remember, our input now is going to end up being y. We're going to input for y instead of x. But let's just talk about a few things before we look at the graph. The domain of this function is always a good place to start. Remember, logarithms typically have domain restrictions. Not always. If this is x squared plus 2, we wouldn't have a domain restriction. We need to check to see that the argument is always greater than 0, because we cannot take a log or a natural log of a negative number or 0. So x plus 2 has to be greater than 0. When we subtract that 2 to the other side, x is the element of all real numbers such that x has to be greater than -2. Here's how it's written in interval notation. The range is going to be all real numbers. That's pretty typical for logarithmic functions. So I went ahead and filled these two in as well. Remember, the vertical asymptote occurs at the value of x that makes the argument equal 0. So instead of setting this greater than 0, I set it equal to 0 and solve, and we get x equals -2 is the vertical asymptote. If you can identify the vertical asymptote right away, remembering that logarithmic functions typically have vertical asymptotes and exponential functions typically have horizontal asymptotes, that's going to help you immensely because you can dot that asymptote in right away. So the x and the y intercepts here. Remember, to find an x-intercept, you plug 0 in for y. To find a y-intercept, you plug in 0 for x. Well, here it is. Let's do the y-intercept quickly first. If I plug in 0 for x, there's not much that simplifies. It's just -3 log 2 plus 1. And just write it in its analytical form. 0 comes in for x, -3 log 2 plus 1. Remember, the base is still 10. We just don't have to write the base if it's log. No base is assumed to be base 10, common log. The x-intercept, you plug in 0 for y. Good thing we did all this. This makes it easy to plug in 0 for y. Plug in 0 for y, you get 1/3. 10 to the 1/3 power is the same thing as the cube root of 10 minus 2. You certainly can find the decimal approximation for these, and it's a good idea so you can compare it to your graph, but just leaving it in the analytical form is fine. I just want, on all of these problems, to make sure that you remember x-intercepts and y-intercepts are listed as coordinate points because we want to ingrain the fact that x-intercept always occurs when the y-intercept is 0, or when the y-coordinate is 0. The y-intercept always occurs when the x-coordinate is 0. So the only difference here is my input now is going to be the y-coordinate. So, remembering this function right here, if I plug 1 in for y, why do I plug 1 in for y? That's the most interesting value of y. It makes the exponent equal 0. It makes this argument equal 0. 1 minus 1 is 0. 0 divided by 3 is 0. 10 to the 0 is 1. And 1 minus 2 is -1 for x. What's the next good point to plug in for y if we move to the right? Well, I don't want to plug 2 in. That gives me an exponent of -1/3. I don't want to plug 3 in. But if I plug 4 in, 1 minus 4 is negative 3. Negative 3 divided by 3 is negative 1. I can do that. 10 to the negative first power is 1/10. Minus 2 is going to be negative 1 and 9/10. That's actually very helpful. This is extremely close to x being negative 2. That's why our vertical asymptote is x equals negative 2. As y gets larger, x is getting closer and closer and closer to that vertical asymptote. So the closer I get to the vertical asymptote, the larger my y value is going to become. Okay? And we found that out by plugging in values for y. Let's go the other direction. I don't want to plug in 0 or negative 1, but negative 2 works well. 1 minus negative 2 becomes 1 plus 2, or 3. 3 divided by 3 is 1. 10 to the first power is 10. Minus 2 is 8. That's another quality point right there. Just by plotting those 3 points, we can get a really good look of what's going on here. I plot the point, negative 1, up 1. I plot the point, back 1 and 9/10, up 4. Really close to that vertical asymptote. And if I dot that vertical asymptote in right away, I can see I'm just getting closer to it. If I go to the right 8 and down 2, there it is. There is a nice logarithmic function. We can see that the range is all real numbers. It goes up forever, it goes down forever. Okay? Next problem. Okay? This would be probably more like what I would put on a test or quiz. Although I like this problem because it has more operations to isolate that x coordinate. This is the same idea, same directions here. But now notice we don't have to add or subtract a term over before I can undo the logarithm. How do I undo a logarithm? Do an exponential on each side. The base is 3, so I'm going to take 3 raised to the y on this side and 3 raised to the log base 3 on this side. I'll end up with 3 raised to the y, but over here, 3 raised to a log base 3 are inverse functions. They undo each other. So I just end up with the argument. If you want to, you can just remember that the little number's the base, logarithm equals exponent, so base raised to the exponent is always set equal to the argument. But we cannot rewrite the logarithm as an exponential until we have a log and an argument only. It cannot have a coefficient, it cannot have terms added or subtracted to it. So we had to do more work in the previous problem to isolate that situation before we could rewrite it as an exponential. This is a significantly easier problem. Add 4 to the other side, there it is. This is a nice exponential form. Okay? So, x-intercept, you plug 0 in for y. Let's just do it right here. 3 to the 0 power is 1. 1 plus 4 is 5, 0. If you plug in 0 for x, let's come back. Look what happens. If I plug in 0 for x, I cannot take the log of a negative number. So I left that positive 4. I crossed that out. There is no y-intercept. None. Okay? So I fixed that. Hopefully it was like that on the solutions that I put. Okay? For you as well. I'm not sure if it was corrected on the actual notes that I put on the website. Okay, working ourselves down. How do we establish the vertical asymptote? Remember the vertical asymptote, we just need to look at when does the argument equal 0. X minus 4 equals 0 when x equals 4. Remember, a vertical asymptote is always x equals the value. Domain. How do we establish the domain? The domain of a logarithm. Set the argument greater than 0 because we cannot take the log or natural log of a negative number or 0. So x minus 4 is greater than 0. Add 4 to the other side. There it is. X is the element of all real numbers such that x is greater than 4. Remember, parentheses 4, comma, infinity, or always parentheses on infinity or negative infinity. The range is going to be all real numbers, so here it is written. We'll see it once we see the graph. But by rewriting it this way, plotting good quality points, now when we get a base of 2 or 3 or 1/2, should be easy to do. The most interesting value of y is 0. The difference is, and I state this every time, input, output, so you can see. The input here is 0, and we already found out that the output would be 5. So what about if y is 1? 3 to the first power is 3 plus 4 is 7. What about if y is 2? 3 squared is 9 plus 4 is 13. That's already off a 10 by 10 grid. So here's 2 good points. But we need to have at least 1 point going the other direction and showing how we're approaching the asymptote. If I plug in -1 right here, I'm going to talk through this. 3 to the negative first power is 1/3. Plus 4 is 4 and 1/3. There it is. Let's plug in -2 and -3. Let's just talk about it so that we can evaluate these quickly. 3 to the negative second power is 1 over 3 squared. That's 1/9 plus 4 is 4 and 1/9. Let's say y is -3. 3 to the negative third power is 1 over 3 cubed. 3 cubed is 27. 1/27 plus 4 is 4 and 1/27. It's getting closer and closer and closer to x equaling 4. That's why we have a vertical asymptote at x equals 4. I expect at least one input that shows a fractional output, so you are indicating how you are approaching the asymptote. I put 2 here, but you're going to have to put at least one of those on tests and quizzes to indicate how you're approaching the vertical asymptote. Okay? All right. Problem number 47. Problem number 47 is another one of these investment problems. We did this in the last section. This says determine how much time, and I wrote it for you right here. Remember, it's the same thing as k times a raised to the t, but the base is always going to be 1 plus the rate of growth or 1 minus the rate of decay. In this problem, we are earning interest. That means that our money is growing. We want to know how long is it going to take for $500 to double to be $1,000. It really doesn't matter if you start with $1 and double to 2. Here's 500. We want to get to 1,000. 1 plus the rate raised to the t. We can add those two numbers together, divide both sides by 500, because I cannot take the natural log of both sides until I have a base raised to an exponent only. Now I can take the natural log of both sides, and I do that because by taking the natural log of the right side allows me to drop the variable down on the same level with the numbers. Remember, this is just a number. It's really the numerical coefficient of t. Divide both sides by the natural log, 1.0475. This is the analytical answer. When you type it into your calculator, you should get 14.936 years. Problem number 48, population growth. So Glenbrook, probably Illinois, I don't know, 375,000 is increasing at the rate of 2.25% per year. Predict when the population will be 1 million. It's the same problem. Here's 375,000. We want to go up to 1 million. We are growing. It's not decaying. Sometimes you could be losing population. Glenbrook is gaining population. 1 plus this number. So I add those together. Notice I divide both sides by 375. I'm taking the natural log of both sides so I can drop down this variable out of the exponent. The natural log property allows me to do that. Okay? I should have written the natural log right here, so that should have a natural log on this side. because I'm taking the natural log of both sides in order to drop this down. It shows up here. I reduce this fraction down to be 8/3, and then I'm dividing both sides by the natural log of 1.0225 to get t by itself. There it is. If you type that into your calculator, you should get 44.081 years. Okay, true, false. Hopefully we'll be done here in about a half hour. True or false? F of g of x equals x, then g is the inverse of f. Justify your answer. The answer is false. F of g of x equals x, but g of f of x must also equal x. That's an x right there. You have to check it both ways. Sometimes it will work one way, but not the other. And a good example to look at is, with the domain restriction situation, that's when you really have to be careful to make sure that it works both ways. Okay, so if you're dealing with like an x squared, and whether it's a positive square root of x or a negative square root of x. 54. Which of the following is the domain? Set the argument greater than 0, subtract the 2 to the other side. X is greater than -2 is written like this. There it is. There's interval notation. Nice, easy. Okay? Multiple choice. Which of the following is the range? Now the range is a little bit different situation, right? We have a vertical asymptote for logarithmic functions. But this natural log function, it's going to go up forever. It's going to go down forever. It's all real numbers. A typical range for most logarithmic situations is all real numbers. Okay, last few problems here, and we'll be done. 56. Which of the following is the inverse? I show the work right here. Now, I do check multiple choice carefully. And if you simply just circle an answer, I'm going to have a problem with that. You should be showing some work. I'm not saying every single step here, but you should certainly be showing this step. X and Y switched. Add the 2 to the other side, divide by 3. There it is. Okay? That's the inverse function. 57. Which of the following is the solution to this equation? This is a great problem. A couple different ways that you could go about this. When I'm solving this equation right here, I added this term to this side first. So I added the -3 to the -x to the right-hand side first. Then I added 1 to both sides. I do not need to take the natural log of both sides in this case. The bases are the same. If I can write the bases to have the same value, then I can just set the exponents equal to each other. 3 is 3 to the first power. That equals 3 to the -x. So I can set -x equal to 1 and just divide both sides by a negative sign to see that x equals -1. You can type it in and say negative of -1 is +1. 2 minus 3 is -1. Works. Okay? But we always want to try to get the bases to be the same first if we can. Okay, that is the solutions to 1.5b. We made a couple corrections along the way, but that should be solid for you now as you look at those solutions to complete your worksheet.